Okay, could you please close the door? Okay, so today we are going to talk about Fourier transforms, or more specifically, we're first going to talk a little bit more about complex Fourier series, because we need to rewrite a little bit the coefficients. So that's the first thing that I want to do, to prepare Fourier transform. Then we talk about Fourier transforms. And this will be relatively short because this is a mathematical task essentially, which is interesting, but not that important from a data analytical viewpoint. And then we're going to talk about discrete Fourier transforms, which is actually the Fourier transform that is always applied when you deal with data and when you evaluate better oscillations to show that perceptual decision making is done by better oscillations or something like that. So that's what is really of importance. And if time permits, we we'll also look at an implementation of that so that you get really the data analytical feeling, because so far this course has mainly been math, but the reason for that was that we need to establish kind of the foundations, otherwise the data analytical things don't make any sense. And then the last topic actually in the whole Fourier analysis complex will be fast Fourier transforms, and this we will not do today. This will be the next session. That's kind of the standard algorithm that is used for discrete Fourier transforms and is implemented in things like NumPy or also MATLAB. And is also the thing that reconstructs the images at the MR scanner. So that will be the last thing, and then we're actually done with the whole Fourier analysis business and can start on dynamical models. So this week and next week, most likely Fourier analysis, and then we switch to differential equations. Good. That's the rough outline of where we are, and maybe let's start with a little bit of a review from last time, and then do one more bit on complex Fourier series coefficients. Is there anything to discuss before I start review? No? Good. Then let's go. So what we discussed last time a lot was the complex Fourier series. So again, the idea is that we have a univariate real-valued function that is periodic and with period t, and we can evaluate, because it also satisfies the Dirichlet conditions, we can evaluate its real Fourier series. If we have the real Fourier series and we computed the a, k, and bk coefficients of the real Fourier series, then we can also rewrite this real Fourier series in terms of the complex Fourier series. And this complex Fourier series is what we discussed last time. That's this series where our index runs essentially over all integers, and we have these coefficients ck, and we express a sine and cosine, so the oscillating functions, by means of this complex exponential, where okay, I do it. Omega 0 is what? Yeah. Omega 0 is 2 pi divided by t, so that's the base frequency, which is defined in terms of the period, and then the different frequencies are indexed by the k, and yeah, we have the complex exponential. What's going on?
What is it again called? This omega 0, which kind of frequency?
Base. And then last time we saw that, or what we actually did is to derive the whole thing if we define the ck in terms of the coefficients of the real Fourier series, and this was done as follows. So for k being smaller than 0, we defined in terms of the ak and bk of the real Fourier series, we defined ck as 1/2 a minus k plus I b minus k. For k being 0, it was defined as a0, and for k larger than 0, it was they are defined as ak minus ibk. Yeah, so this are the real Fourier series coefficients, obviously. So the whole thing of expressing a function in its complex Fourier series representation in this scenario that we discussed last time rests on the availability of the real Fourier coefficients, because if you have evaluated the ak and the bk for all k, then you can evaluate all the ck, and then you can put the ck into the complex Fourier series, and then you can write the function in its complex Fourier series representation. There is, and this is what we will need for the Fourier transforms, there's also a direct way of evaluating the ck, so the coefficients in the complex Fourier series representation. And that's not that surprising, because obviously the ak and bk, they are given in terms of integrals with the cosine and the sine function, and one can, of course, rewrite the cosine and the sine function in terms of a complex exponential. So there's also a complex exponential form of the ck coefficients. And this is what I want to introduce first. And that's what I'm going to do now. So this is now the scenario that you didn't evaluate the real Fourier coefficients, but you just have a function f. And so you essentially don't have this, so let's get rid of it. You don't have this, and you want to compute the ck directly without recourse to the real Fourier coefficients. So they are not there. And then these ck can also be evaluated as follows. So if you remember the AK and BK formulas, they are very similar. So instead of having the complex exponential in there, we had the cosine and the sine in there, and we evaluated, and we came up with these formulas because of these orthogonality properties of the cosine and sine functions for different frequencies. Here we don't have AKs and BKs, but we have only the CKs, and the complex exponential obviously has both. If you think of Euler's formula, which you should always have in the back of your head, then it's not so surprising that this term here can account for cosine and sine functions. But how, I want to also show that explicitly. This is now, if you have studied again how the AK and BK came about, this is completely the same logic, and I just go over it so that you have seen it. So the question is, why do these coefficients here, CK, if we compute them directly in terms of the function without recourse to the AK and BK, why do they have this form? So that's the question. And yeah, to show that the proof works essentially identically to the ones that we've seen for the real Fourier coefficients. Does anyone remember how that worked? So how that proof procedure worked? So what was required and what did we then do? And what was the magic? No, the orthogonalities, they played a role, but how did this procedure work to evaluate the real Fourier series coefficients AK and BK?
I think for the cosine, we just add a sine. Or was that another procedure?
Yeah, roughly, but so we did things. And we started with the cosine and sine orthogonality properties. So that's Euler's formula. So does anyone remember that? I think this might actually be a study question. So in terms of, not in terms of writing it up, but in terms of knowing the steps that went in there. Okay, so no one remembers. Try to study this and not only prepare your presentations for the courses. Thanks. Because otherwise you will be lost at one point if you're not already lost. Okay, so the way that these things always worked was that we established some orthogonality properties, and then I think that's what you meant, then we multiplied the function and the series formulation with cosine or sine, and then we integrated, and then based on the orthogonality properties a lot of things went to zero so that we could solve for the coefficients. So that was the procedure that we did for the AK and the BK. Are you searching for that on your cell phone? Or I know it's on the cell phone anyway. Sorry. Okay, and we will use the same procedure now. So we will start with an orthogonality property. So again, we will look, or we will establish we establish some orthogonality property. Which in this case, so the whole thing that we're doing right now is just expressing the same thing essentially, instead of directly in cosine and sine, expressing the whole thing with complex exponentials. So we have the following orthogonality property. If we form the integral from minus t half to t half of a complex exponential with frequency n omega 0x times a complex exponential with frequency m omega 0x dx, so that's the integral, then this integral is 0 if the n doesn't match the m, and it's t if the m matches the n. And this follows fairly straightforwardly from the trigonomic orthogonality properties, so from the sine and cosine orthogonality properties that we established like 3 or so sessions back. The thing with if they are the same, then of course it's really easy to see that the whole thing is t, because then if n equals m, then we have here we get e to the power of 0, which is 1. So we have the integral of the function of the constant function 1 from minus t half to t half, which is t. So that's really easy to establish. That it's 0 if n doesn't equal m. I updated that in the script and wrote it out, but it's relatively straightforward to see where this is coming from, because based on Euler's formula, this is essentially, let's make it a little bit shorter, this is cos I n x plus I sine n I, oops, not I, what? nx plus I nx. And if and this is essentially the thing with m, and then if you think that you're multiplying things, so that you multiply cos nx times cos cos n x and so on, so that you write out these things in terms of the cosine and the sine, and then form all the multiples, you will get to these multiples of cosines of different frequencies, cosine and sines of different frequencies, and sines of different frequencies. And then if you use the linearity properties of the integral, this splits up, so you get 4 integrals essentially, and all these 4 integrals will be integrals that are exactly the integrals we have in the trigonomic orthogonality properties, or the sine and cosine orthogonality properties earlier on, and then everything is 0. So this is in the script, but it's also a good exercise to basically again think about first of all Euler's formula and linearities of integrals. So this is in the script now, but you might I hope you see that in a way already from this, because it's fairly straightforward. It's also a good exercise. Okay, so we basically take this orthogonality property now as a given, because essentially it dates back to the, or it derives from the sine and cosine orthogonality properties. And then we do the same thing again as we did for the real Fourier coefficients. So we start with the expression for the complex Fourier series. So we have this. Yeah. And then we do the same thing that I asked earlier about, that we did for the real Fourier series coefficient. So we multiply with an arbitrary frequency m omega 0 x, both sides, so that we get fx e minus I m omega 0 x. And we get here there. And then the next step was to integrate. So we put up integrals over the interval minus t half to t half. And then we again assume that it's allowed to exchange the order of summation and integration, so that we get these integrals on the right hand side. And then we can use this orthogonality property. So all these integrals here are 0 except when k equals m. Yeah, so k, remember, k is the running index. So k goes from minus infinity to plus infinity. And at one point it is m. M was chosen arbitrarily. If it's not m, everything is 0. So all these terms in the sum come out 0. But if it's m, then we get the integral minus t half cm e I m omega 0 x e minus I m omega 0 x dx. And then the cm does not depend on the integration variable, so we can take it out of the integral. That's again linearity properties of integrals, as we discussed quite early on. And then we just established that this, I mean, it's also easy to see without even establishing that. So this, if you put the exponential together, you get e to the power of 0. Again, you need to integrate over minus t, so that's 1. You need to integrate over minus t half to t half, so that's t. So you get cmt. And then one can solve for cm, so that we end up with cm equals 1 over t, and there we have the left hand side, so we have minus t half fx a minus and then I m omega 0 x dx. So this shows that one coefficient in this complex Fourier series for m is given like that. Now our m was arbitrary, so we can also call our m k. Of course, then we should call this running index something else if we do this derivation, but now we don't need to do this derivation anymore because we've already did it. So we have shown that this holds. Yeah, so it's essentially the same thing as for the real Fourier series coefficients, only that things are expressed with complex exponentials now. Yeah? Happy?
Just one thing I don't get, why this e to the power of I m omega 0 x times e to the power minus minus I is e to the power of 0.
Okay.
I didn't quite.
So that's if you go into the early parts of probabilistic models for functional imaging, there is some stuff on the exponential function.
And so it's a form, because maybe
yeah, it's so the exponential of 2. So if you have the exponential of a times the exponential of b, that's exponential of a plus b.
I see. Okay.
So if you have something like I to the power of minus k now, or not k, let's say minus x. To the power of x, that's then e to the power of minus x plus x. This is e0, and that's 1.
Thanks.
Yep, no, but it's a valid question. It's kind of things one either knows or doesn't. Okay, other questions? Okay, good. So that was kind of a last remaining things to say about the complex Fourier series because now we've transferred everything essentially from the sine and cosine, so things that you know from school, to the complex exponential writing that people like in the technical literature. Though I'm not quite sure why they like it so much, but they like it. I guess it's easier in certain scenarios. Good, but now we've actually are really done with serious representations of functions and can talk about Fourier transforms. Yeah? So we stop talking about series now and start talking about Fourier transforms. And the first thing is that we talk about the Fourier transform. And the important thing, in addition to some details here, is that you learn to use these terms appropriately. Because there is, if you talk to cognitive neuroscientists, there's always horrible confusion in terms of the terms. Because a Fourier transform is something different compared to a discrete Fourier transform, and a fast Fourier transform is something completely different from a Fourier transform or a discrete Fourier transform. So if you don't like the math or whatever, please at least learn the differences between these terms, because the fast Fourier transform is an algorithm to evaluate discrete Fourier transforms, which we will talk about next time. The Fourier transform is an analytical entity that allows us to do what we discussed from the very beginning. So we have a function, a univariate real-valued function f that has some interesting form. So that's our fx, if you want. So fx being the values, f being the function. And now we want to re-express f in terms of another function, but on a different domain. So here we have the domain x, which, for example, models time. If you are doing e.g. Oscillation analysis, to find that emotions are represented in gamma band or whatever, if you do a classifier on them, and or space, if and this is what we will need this for in January, if we are talking about magnetic resonance imaging. So that's the domain here, and what we set out in the very beginning is that we want to express the same thing in terms of another function that extends over frequency space. Yeah, so we want to associate with it some frequencies, and I'm now drawing some other function here. However, one also should be aware that this is another function, a big F omega, but what is actually shown here, because this function takes on complex values, this is only, for example, the absolute value of this function. So in principle, what we should plot, and what one of course also can plot, is a function on a 2-day grid where we have the real and the imaginary part. But this will make sense when I show you the formula in a second. But yeah, this should be kept in mind. Nevertheless, the important thing is that we get from a time or space domain to a frequency domain, which everybody wants if one wants to do MR imaging, or if one wants to do, for example, EEG analysis, even basic EEG analysis, if you want to, for example, filter the data. Now, however, this is again then in the discrete domain. Anyway, we are now in the continuous domain and talk about the Fourier transform. So we have a function f, and then the Fourier transform of f is defined as the function f, which is also This is not quite right. Oh, this must be complex. Which is a function from the real numbers omega to the complex numbers, not the real numbers as I have it in the script. And these omegas are frequencies, and each f omega is defined, and this is the important part, is defined as the integral of the function fx times the exponential of minus 2 pi I omega x dx. So how this works is that you have a function f, you know how this function looks, and if you want to evaluate the Fourier transform, you need to multiply each value of the function f with this complex exponential term and integrate over all x. And you do that for all omega, and then you get something out that depends, of course, on how the function f looks and the integral that then comes out. We will not, and this is already here the important message, we will actually not do these integrals. So this is something that you can do in math, and you're very welcome. And in books you will always find some examples for Fourier transforms of functions. We will only use this essentially as the inspiration for the discrete Fourier transform, which I want to do directly afterwards. However, this formula for the Fourier transform, which is, if you open a book on Fourier transforms, is the first formula that you see. This is, of course, motivated in terms of these coefficients in the complex Fourier series. Yeah? So I write these coefficient formula down here to kind of make this intuitive, although mathematically this will be hand-wavy. So you've just seen that the coefficients, so the ck, maybe I write that here, the ck in the complex form of the Fourier series are of this form if I now don't write e to the power of but x because it looks nicer in this context, and I also don't write omega 0 but instead write the 2 pi divided by t out again. So so instead of omega 0 I have 2 pi divided by t here again, and the dx. Yeah, so this is just what we've just seen like 5 minutes ago. This is the coefficient in the, maybe I write that here, coefficient in complex Fourier series. For k from minus infinity, if something like this would be possible, to infinity. Yeah. Now the hand-wavy mathematical idea, this so to really establish this mathematically, this would actually first of all I never went into the full mathematical details of this, and the other thing is it would also require a lot of things that really are not important in terms of data analysis. But the hand-wavy way to explain this correspondence is that if you imagine that the period of the function is going to infinity, yeah, then these boundaries of this integral, because t gets larger and larger, also with respect in the negative direction and the positive direction, go to infinity. Yeah, so you see somehow that maybe I put this there, that if you allow the period of the function to become infinitely long, then these CK coefficients start to look like the Fourier transform values for this frequency omega in terms of the boundaries of this integral. And also, if you think that these k, they are integers and they get divided by ever increasing numbers. So these k divided by t get smaller and smaller in terms of their extension, if you want, or their measure, and they become these omega. The whole thing is very hand wavy, so Yanis, don't go crazy if you or anyone who has some mathematical experience, because you would also start to wonder what's happening with this t. If this goes to infinity, then this goes to 0. So I think the only way one can actually address that properly is in terms of measure theory, so that these things make sense, but we will not do that. So we will use the hand wavy way, which is completely enough for what we want to do with this, because we will go to discrete Fourier transforms in a second anyway. So the intuition here is that the definition of the Fourier transform of a function f, so this thing here, which defines the values of the Fourier transform big F of a function small f, corresponds to something like the discrete coefficients in the complex Fourier series of a function f, if you, instead of basically going over integers, so here you have k being the integers, go to omega being real numbers. Yeah. So here you have the k's going minus 100, minus 99, minus 98, and then at one point you're positive 10, 11, 12, 13. And for each one you evaluate this frequency contribution term, ck. And if you're in the Fourier transform realm, your indices are real numbers. Yeah, so you have many more. So you have, for example, if instead of 10, 11, 12, you have 10.00001, 10.00002, and so on. Yeah. So that's kind of the hand wavy way to motivate the form of the Fourier transform. Yeah. But the important thing is that, like these things, the CK measure the content of frequencies. So, for example, remember again that we set our CK. We can, for each CK, we can compute the real part, which was our AK, and the imaginary part, which was our BK. And then from this we can, for example, evaluate the magnitude AK plus BK of a given frequency. So this is how the CK encode frequency magnitudes. The same way these F omega, which are in general complex numbers, encode frequency magnitudes. Yeah. To now, what we don't do, because I don't see the point in a data analytic context, is to actually now sit down and compute the Fourier transform of some function. Yeah. So if you open some Fourier transform book, you will find that then, I don't know, what do they usually compute Fourier transforms of? I think, for example, of boxcar functions or of Dirac delta functions. So functions like this, so if this is f, or functions like this. You can find explicit formulas then for the Fourier transform. It's interesting, but it's not something that you will encounter in data analysis often. So we will essentially only talk about Fourier transforms for the next remaining 4 or so minutes, and then we do discrete Fourier transform. Yeah, but this is the Fourier transform. Fourier transform, actually, if you're doing data analysis in cognitive neuroscience, you never do Fourier transforms. You always do discrete Fourier transforms. Yeah?
When do you do Fourier transforms?
When? Yeah, if you want to study things in an analytical setting, so for example, I think one example is if you want to achieve something in frequency space. So what I haven't told you is that with the Fourier transform also comes the inverse Fourier transform. So you can also go back here, and let's say you want a certain pattern in frequency space that you specify explicitly. So for example, you want some frequencies on and all other frequencies off. And you want to achieve this by using a certain function in time. And then you might want to do this analytical transfer between a function and its Fourier transform and backwards from its Fourier transform to the time domain, so that based on this analytical model, you know what to do in terms of specifying your signal. So that's a typical engineering application. But doing Fourier transform in terms of data analysis doesn't happen unless, so because in data analysis you always have data points and you don't have functions. If you, unless you fit maybe a function to your data points and then say, okay, this is my function of which I form the Fourier transform. So in kind of more involved modeling, it might actually sometimes be helpful to know how to compute the Fourier transform explicitly, but in basic data analysis, cognitive neuroscience, Fourier transform doesn't happen. What happens is discrete Fourier transform. Okay, then let's have a break and then go to discrete Fourier transform, the actual thing, and actual data analysis in the next hour.
Yeah,